Hello. Now we will be talking about the use cases and look at two specific use cases, and we'll go through a walkthrough as to how data is collected from these use cases, and eventually we'll go to the other aspects of transmission, storage, and processing. So the two use cases are the first one is a very common one, which is about search engine, and the second use case is about industrial AI or an enterprise AI. Now, search engine is something that all of you are very familiar with. We use it in our day-to-day lives whenever we search for an app on our phone, whenever we search across the web for a particular keyword, searching on Stack Overflow, and so on and so forth. There's just limitless ways in which search works just amazingly for us. So how does it happen actually? Now, if we look at from a consumer perspective of search, the user lands on a particular web page or an application, and they typically see a search bar wherein they write their query and then press an enter button. Now, when the enter button is pressed, the query is sent to the backend search engine, wherein various kinds of processing can happen over the query. One of the processing is to understand the intent of the query based on what the query is, and there are sophisticated machine learning models that can help you understand what the intent is. Now, once the intent is understood, the query is probably reframed or augmented with additional information, and then this query is sent to the actual information retrieval engine in order to retrieve the most relevant results. A typical information retrieval engine works on statistical methods. Using the most popular one is term frequency and inverse document frequency, and it tries to match the provided keywords in the indexed documents that it has. Now, indexed documents are any document on which the search is supposed to run. So if you are looking at a web search engine, the indexed documents are an index of all the web pages that the internet has. Similarly, if you are looking for an email search, then the documents that are indexed are your emails, which includes a lot of information. For example, where it is coming from, when it was sent, what are the attachment, what are the contents, and so on and so forth. Now, these documents are indexed in a specific manner which aids in fast retrieval when a particular keyword is presented to the information retrieval engine. Now, once these results are retrieved from the index, these results needs to be ranked and then presented to the user, because there is only a limited amount of screen space available on whatever device the user is interacting with. So one would want to present the most relevant results first to the user. And the definition of relevance is subjective to every user. For example, some users might want to view a particular results from a specific geography, versus there are other users who would want to view the results from any geography. So this still can be done as some sort of a naive or basic filtering of the results, but there are more specific preferences. For example, when you are looking for a certain keyword, there may be certain users who would prefer a different kind of results versus others looking for a different kind of result altogether. Now, this ranking is where a machine learning model comes into picture. The common genre for these machine learning algorithms is called learning to rank. Learning to rank algorithms are specifically designed to understand the user's preferences and to be able to rank a particular result based on that particular preference of the user. Now, these preferences are most oftenly not stated directly by the user, but have to be interpreted based on their interaction with the particular system. So let's take a deep dive into how such a system can be built. So when a user performs a search on your system or any system in general, typically it begins with a user ID. If it's a logged in user, And if it's a non-logged in user, then there is no concept of user ID, but you can still, for example, associate certain unique IDs with every non-identified user, so that there is still a possibility of tracing or associating queries to a particular individual and to rank it accordingly. Now, this user ID or whatever ID we use to uniquely identify our user is associated with a particular query that the user has done. Now, this query is also associated, this query is assigned an ID when the user performs that search. And typically the pair that is looked forward is called the user ID and query ID pair. Now, once this user ID and query ID pair gets to your backend search engine, then one of the first things that will happen is that skipping the query intent part for now, but otherwise one of the first things happen is to split the query, to send it to your information retrieval engine and get the results back. And these results are typically stored for further purposes that we'll look at it later. And then these results are ranked again according to the learning to rank algorithm, and these re-ranked results are then stored again. So now you have your original results and your learning to rank results, and the learning to rank results are then presented to the user. Now, when a user is presented with these results, there are a few things that the user will definitely do. He or she might want to scroll through all the results that are presented, and then based on a bird's eye view of all the results that are presented, they might want to proceed with one or more of the results. Now, when the user clicks on a particular result, there are certain ways in which we can track what result was clicked in response to the query, and this information can be tracked very easily, for example, using tools like Google Analytics or Mixpanel, which provide a very easy interface for you to embed JavaScript snippet into the front end, and then they automatically capture most of the information about user behavior. But if there are additional information needed, there are ways in which that can be done as well. On the screen on the right hand side, you see a developer console from a browser, and it shows how Google Analytics is being used to track various information. Now, let's say that the user clicked on result 1, result 3, and result 7. So this information is captured as soon as the user clicks through, let's say, Google Analytics. And now what happens when they visit those results respectively? You would want to typically understand what user do with that result in order to assess if they were able to satisfy their search based on the interactions that they did. For example, if it's a web page or if it's an e-commerce product that they are looking at, you would typically want to see how much time the user has spent and on which specific areas of the web page, and what did it lead to. For example, if it's an e-commerce, did it lead to the user adding that item to their cart or checking it out, or they simply browsed another result and closed that particular tab. So all these information are again captured through the client interactions. And when I say client, I mean a desktop or a mobile client. For example, your browser could be a client. The application on your iOS or Android phone is another example of a client through which the user is interacting with your system. So using these methods, we capture all these information, and we persist them in a manner that makes it easy for us to process these information later and to be able to come up with meaningful insights. So another example that you can see here is a different link from slideshare.net, and this is the link that is presented to you when you see the results of a particular search that has happened. So you can clearly see that there is a query ID that is associated with the document, and there are some additional query parameters that help augment this information. Okay, so that's how you collect the information about user engagement with your particular system. And this can go to any level of detail and any level of sophistication that you want it to be. The next use case that we will look at is an enterprise industrial AI use case. In industrial AI use case, we typically have to cater to the data that is coming in from various industrial systems. For example, there could be a manufacturing facility or a factory that has a lot of machines in it, and each of these machines have different sensors associated with them that emit data about the state or the condition of the machine at different frequencies. Now, based on this data, one would have to, let's say, predict if the machine is going to fail in next a couple of weeks or not. So this becomes a classical prediction problem. But in order for anybody to build and deploy this entire system, you need to have an end-to-end pipeline wherein you are able to ingest the data, then process, store, and feed the analysis or inference back to the machines. So on the right hand side, the diagram that you see is taken from Quartic.ai, which is a leading industrial AI platform provider. And in the bottom, we can see that there are various kind of protocols. For example, Modbus, Allen Bradley, OSI Pi, Historians. These are the various protocols through which factory machines are connected and they are sending data. Now, all these protocols might be totally new and unheard of, but fundamentally what it means is that there are these different kind of servers, and these servers emit data, or they push data, or you have to poll from these servers in order to get the required information. Now, the thing is, how do you actually connect to these servers? What protocols do they use? So a lot of industrial servers in operation right now have their proprietary protocol, and some of them actually use the more recent advanced ones, use new protocols, for example MQTT or other pub-sub mechanism. But otherwise there are many protocols that use their proprietary protocol, and they do expose their SDKs and APIs. So what you will eventually need to do is to write a software program, and that program should be able to connect to this server and either poll for the data or subscribe to the data that the server is sending. Now, subscription and polling are something that we will also talk about going forward in the data transmission aspect. So if you don't understand them, that's completely fine for now. Just imagine that this is some way of communication in which you will have to fetch data from these servers. And when you're writing such a program about connectors, in all likelihood, these connectors are going to be a service daemons, which means that they are running as background processes in a computer system, and they are working round the clock and fetching data from those servers or sending data to them. And when you actually start writing them, you will figure out that in most of the cases it needs to be a multi-threaded, multi-process daemons, because there could be a lot of data that you would want to capture from these servers, and depending on what speed are you capturing this data, you might need a multi-threaded environment. For example, if you are supposed to capture data at every 5 milliseconds from an array of 1000 odd sensors, you can see that if you make an HTTP request to that server, and the response time that it gets and the time that it takes for the computer system to actually process and transmit it is going to be much higher than 5 milliseconds in most cases. So what you would typically do is to create a pool of threads, and each of these threads will be able to establish a unique connection with these servers and fetch the data at required interval, perform its processing, and then return that thread to the pool so that any other any other trigger of the data fetch can use these threads from that same pool. So that is one way in which multi-threaded programs can be used here. But yes, depending on use cases, there can be more complex scenarios as well. On the lower right hand side, we see other connectors, for example, SAP, Oracle, IBM. These are the kind of connectors that holds your enterprise data. For example, how's your workload looking for the rest of the week, or what are the consumer complaints that you have received for a particular product. And sometimes we need to fetch data from all these various different sources, put them together, contextualize it, and then run a machine learning model to make sense of what is happening with that particular system or a process at a high level. So this is an example wherein we have various different kinds of data that will fall into one place, needs to be contextualized, and this is where the schema of data becomes particularly important. Because if you look at the earlier use case about search and in general any Web 2.0 client interactions, the schema is provided by the schema provided by tools like Google Analytics or Mixpanel is pretty generic and can accommodate a wide variety of data structures that are suitable for most of the needs. However, in industrial scenarios, you will often find that the data structures in which the data is returned by these servers are not the same as what your client application or what your consumer application requires. So in that case, one would definitely need to convert this data from one format to the other format. And when I say format, it doesn't necessarily mean format. It also means format plus schema changes. So the data needs to be transformed into a different schema so that it can be easily accommodated and flows with other data that are coming in from various data sources. And having a common schema helps the entire data engineering team within an organization be able to consume that data more efficiently. Now, in general, in a large enterprise, there are so many different kinds of data that is being sent or used. There are various kinds of schema that a particular application demands, and deciding a good schema for any data processing is one of the most fundamental and most important thing to do.